first comment on chemistry is this. You need to understand some base concepts of chemistry if you're going to understand how all the rest of this stuff works. Like if you're going to understand how you have muscles and how they function, you got to understand proteins. If you're going to understand proteins, you got to understand hydrogen bonding. If you're going to understand hydrogen bonding, you got to understand the concept of covalency. If you're going to understand covalency, you need to understand atoms. And if you're going to understand atoms, you got to understand subatomic particles. So let's proceed. Let's go down this rabbit hole, see where it takes us. Now, this is a nice breakdown of things that I would know if I were you. I'd feel free to give that a read. I'm going to jump right over to here. My first comment is that in the world around us, there is matter, there is energy. Matter is anything that occupies space, has mass. You can touch it, feel it, smell it, what have you. It is matter. Energy is non-tangible. Okay, it's not something that we can see, touch, or smell. Energy is only visible, if you will, in its effect upon matter. Energy is defined as the ability to do work. Okay, the ability to put matter into motion. Now, energy comes in a variety of forms. Normally, we classify these into kinetic and potential energy. Kinetic energy is energy of motion, whereas potential energy is a storage form. But the reality is there's a lot going on here. There is chemical energy. Chemical energy is energy that's locked up in chemical bonds, like ATP molecules, adenosine triphosphate, that form your energetic molecules. That is chemical energy. You burn ATP. Hearing me right now, you might be burning ATP, typing something or writing something. If you get up and you walk across the room, you're burning ATP. That is chemical energy. Okay. Electrical energy is that which moves as a particle flow, okay? Movement of charged particles. Your nervous system functions off the principle of electrical energy. The light bulbs around you function off the process of electrical energy. Mechanical energy is that directly involved in doing work. We've got our buddy Einstein here pedaling a bike. That's mechanical energy, the energy of motion. And then there is radiant energy, or what's often coined electromagnetic energy. This is energy that travels in waves. That's light, okay? Like the infrared light, which is basically heat, microwaves. Yeah, man, it's all radiant energy. The light around us, it's all radiant energy. Let's just keep on rolling. All right, here we go. Now, in the world around us, there are a lot of different elements. You've seen the periodic table of elements. You are somewhat familiar with this: hydrogen, helium, lithium, beryllium. You get the concept. You know what we're looking at here. What I need you to know is that there's about 6-ish elements that make up the vast majority of your body. Almost your whole body is oxygen, carbon, hydrogen, nitrogen, calcium, and phosphorus. And that makes perfect sense. Now, why so much oxygen? Why so much hydrogen? What's your body mostly made of? Water. And if water's chemical formula is H2O, it means there's going to be a lot of oxygen, a lot of hydrogen in your system. Why so much carbon? You are what we call carbon-based life form. All your proteins, your lipids, your nucleic acids, they're all built out of carbon backbones. So you're going to have a whole bunch of carbon in your system as a result of that. Nitrogen, calcium, phosphorus. You think about your skeleton being a lot of calcium and phosphorus as an example. Nitrogen is a major building block of your system. That sort of makes sense. So you got 6 elements that make up the vast majority of your body. Now, all of these, generally speaking, have protons, neutrons, and electrons. What makes them different? The numbers of protons, neutrons, and electrons. Okay, the numbers of them make them different. Protons are positively charged subatomic particles. It looks something like this. So here is a carbon atom. It's got its protons and neutrons here in the center. That's called the nucleus of the atom. The center of the atom is where you find the protons and neutrons. The electrons flow around the outside of the atom in what are called energy shells. Okay, energy shells. So your positively charged protons are in the center. Your neutrally charged neutrons are in the center, and then your negatively charged electrons are orbiting around the outside. Okay? Electrons, negative charges on the outside, protons positively charged in the middle, neutrons neutrally charged in the middle. And generally speaking, you're going to have the same number of protons as electrons. Neutron numbers can change, Protons and electrons, they tend to be the same number in nature, in naturally stable molecules. Now, I want you to know a little bit about this too. So in a periodic table entry, you need to grasp that, like Na here is for sodium, that's the atomic symbol. I might ask you, what is that? You have to tell me it's atomic symbol. I'll never ask you to tell me, which element is which. That's not something I'm concerned with. That's chemistry. But I might ask you if that's what that is in this atomic symbol. I might ask you what the atomic mass is. Like for instance, here for oxygen, the atomic mass is 16. Now, what does atomic mass mean? That's the number of protons and neutrons. Okay? As it turns out, protons and neutrons have mass. They weigh 1 atomic mass unit each. So if I say, here's oxygen, what's its atomic mass? You'd say 16. 16 is the number of protons and neutrons. The 8 at the top here, that's the atomic number. The atomic number is just the number of protons. So let's lay this out one more time. Protons, neutrons, and electrons. What are their charges? Where are they found? What's an atomic number? What's an atomic mass? Atomic number is the number of protons. Atomic mass is the number of protons and neutrons combined. Let's go here. All right, when matter combines, indeed. So let's see, what do I want to say here? Let's just get through most of this and jump straight down to here. There are 3 major types of chemical bonds. These are ionic, covalent, and hydrogen bonds. And hydrogen bonds are kind of like a side effect of covalent bonding. All right, first things first, ionic bonds. So ionic bonds are where one atom thieves away an electron from another atom. Okay, one atom thieves the electron away. Now, I said that in nature, atoms are electrically stable. They have the same number of positively charged protons as they have negatively charged electrons. But what will happen in an ionic bond is an atom like sodium will donate an electron to an atom like chlorine. And if sodium loses a negatively charged electron, it was stable before, now it's lost a negative charge, it becomes overall positive. Chlorine was stable. It had the same number of protons as it had electrons, the same number of charges. But now it's gained a negatively charged electron. So what happens to chlorine? It becomes overall, negatively charged. Because sodium is positively charged after this interaction, and chlorine is negatively charged after this interaction, they stick together like magnets. That's an ionic bond. They ionize. They change electrons. Ergo, they stick to one another. They're ionically bonded. That's how this works. Covalent bonds. All right, there are 2 forms of covalent bonds in the world around us. These are referred to as being nonpolar covalent bonds and polar covalent bonds down here. All right, what this means is, hang on, let me say this. A covalent bond is a system where there is a sharing of electrons. The electrons are shared. You're not thieving one away from the other, you're just sharing them. The 2 atoms are going to come together, they're going to share their electrons, just hanging out with one another. But, as is the way of things, sometimes you share equally. It would be considered a nonpolar covalent bond, and these are nice symmetrical molecules, I should say. Nice and symmetrical, nonpolar covalent, equal sharing, versus polar covalency. In polar covalent bonding, the sharing is not equal. The electrons hang out around one side of the atom or molecule more than they hang out on the other side of the molecule. And if the electrons are hanging out on one side, what's the charge on an electron? Electrons are negative. If they're all hanging out on one side of the molecule, that side of the molecule takes on a net negative charge. So then the opposing side of the molecule takes on a net positive charge. Okay? Now, that means that this whole molecule here, water, made up of 3 individual atoms, that whole water molecule is polar. It's got a positive side and a negative side. And what's going to happen if I bring together two water molecules that are polar, they attract each other. They attract each other. And you've seen it. You take water and you drop it on a table, or you see a car that's got a good wax job, water gets on the hood. Does it just go flat? No. You take water and you drop it on the table and it beads up, because the water molecules, the individual molecules within that, are attracted to one another so strongly that they pull together and bead together as one. All right? They don't just go flat. Put a drop of oil on the table, it's going to go flat. A drop of water pulls together because the molecules attract one another. You may have heard the phrase oil and water don't mix. The reason oil and water don't mix is very simple. Water is polar covalently bonded. It displays hydrogen bonding. That's what this is, folks. Hydrogen bonding is a weak attraction between polar covalently bonded molecules. Hydrogen bonding, wherever it is, right there. Gives water, as an example, unique attributes. Oil molecules, nonpolar. They are nonpolar covalently bonded. Ergo, they are chemically incapable of bonding to water, to polar molecules. That's why oil and water don't mix. Check out this animal here. This is a water strider. It's an aquatic organism. If you look, it's actually standing on the top of the water here. This is water. So it's capable of standing on what we call the water's tension. In other words, those individual molecules of water are attracted to one another strongly enough that this lightweight organism can stand on the tension generated. It'd be like you standing on really thick jello or something. Okay? Same concept. Again, this gives water some unique attributes that we're going to get at in just 1 second. All right, and that takes us to biochemistry. All right, biochemistry. So what we are doing here is we are looking at the atoms, the basic chemical composition, how living things, how biological things are built, the molecules that we must have to survive, and go through and discuss those a little bit. Now, in the realm of biochemistry, we have what are referred to as inorganic molecules and what are referred to as organic molecules. And both of these are very important for us. They're just different, okay? They're just different. Inorganic molecules tend to be really small, okay? Just a few atoms in most cases. Inorganic molecules tend to lack carbon. They tend to be non-carbon containing. There are some exceptions to this rule, like carbon dioxide, which does indeed contain carbon, but it's very small, just a few atoms. These are going to be things like salts and acids and bases, water being the quintessential inorganic molecule out there, whereas organic molecules tend to be incredibly large, okay? Hundreds and hundreds of atoms. Massive, massive molecules, and they will always contain carbon, okay? Covalently bonded carbon, typically in big long chains or rings or what have you. Massive carbon-based molecules make up you a carbon-based life form, organic molecules, okay? When we're talking about organic molecules, we're talking about nucleic acids and proteins and lipids and what have you, okay? The major molecules that make you who you are. Now, the most important inorganic compound by any stretch of the imagination is certainly water. Now, it's pretty obvious as to why water would be very important for you. You are indeed mostly water. Your cells are mostly water. So as a result of this, because your cells are mostly water and you as a whole are mostly water, that means that the unique chemical properties of water tend to be your unique chemical properties. This is incredibly, incredibly important. Things like a high heat capacity. Water has the ability to absorb and release lots of heat before it physically changes temperature itself. All right? It means it takes a lot of energy gain or a lot of energy loss to change the temperature of water. And why is that important? It means water is thermally stable, which means you are thermally stable. It can be freezing cold on a Tuesday night, and I'm sitting in bed. My wife says, "Got to take trash out." and I can throw a jacket on with my shorts and nothing else, you know, and run outside, take the trash out and get back in the house, even though it's freezing cold, because I'm not going to go into hypothermia. I'm not going to die from heat loss, because my body being mostly water means that I can go out in the cold and not lose substantial quantities of temperature, not have my temperature drop by a substantial number, if that makes any sense at all. Probably my core temperature won't move at all in the grand scheme, because being mostly water, we are thermally stable. We have a high heat capacity because water has a high heat capacity. A high heat of vaporization as well, because it takes let me go back and say it like this. It takes a lot of energy to make water change states. So to take water from a liquid and turn it into a gas, liquid to gas, takes a massive, massive amount of energy influx. Now, that's also good for you, because if water has a high heat of vaporization, that means that the water in your system has a high heat of vaporization. And the roundabout importance of this is that when you sweat, if you get hot and you sweat, and that sweat boils off your system, which is what's supposed to happen, it liberates massive quantities of heat. Okay, massive quantities of heat. Lots of energy leaves your system. If you go to an arid area, an environment that doesn't have a lot of humidity, like in Alabama here, it gets hot and humid at the same time. So you go outside and you get hot and you just sweat and it pools all over you and you feel disgusting. But if you were in a arid environment, like for me it was Santa Fe, New Mexico is where I really first noticed this. It's completely dry out there. And you walk around, you stay in the shade, and it feels wonderful. You feel like $1 million. It's like, oh my gosh, it feels so good outside. And then you see that it's like 110 degrees within reason. It's very hot indeed. If it was that temperature here in Alabama, you'd feel like you're gonna die. But there, because it was very arid, there wasn't a lot of humidity, you felt great. Because when you would sweat, the sweat would immediately boil off your system and liberate lots and lots of heat energy in the grand scheme, okay? Wonderful, wonderful for us. Water is also highly reactive. Water participates in what are called hydrolysis reactions and what are called dehydration synthesis reactions. Now, pay attention, folks. Lysis, the root word lysis, means to break something down. So if it's hydrolysis, hydro means water, hydrolysis means to break something down using water. That's how all of your digestive enzymes function. When you eat a hamburger and you break it down into individual parts and pieces in your intestinal tract, those are hydrolysis reactions. By comparison, water also participates in what are called dehydration synthesis reactions. Synthos means to build or to make one or to bring together, okay? Synthesis means to make something, and it's dehydration synthesis. So what are we doing? We're pulling the water out and making something as a result. If I don't know. Okay, let's go classic example. I cut myself, okay? I cut myself. To heal that, I need amino acids to make protein. Where do I get amino acids from? The food I eat. I eat the food, I break it down into its minor subunits by using hydrolysis reactions. That gets into my bloodstream, flows around till it gets to the area where it's needed, and then dehydration synthesis reactions are used to make the proteins necessary to bring about healing. This is incredibly important. And water is also a polar solvent. I'm not as concerned with that at this particular stage and in this class, so let's not worry so much about that. Let's keep on rolling. All right, pH. Other very, very dyslexia. I live with it every day, folks. You'll see as we progress through this that I sort of like to mix up where words go in sentences and a whole variety of other things. Okay, you'll see. Where am I at? pH. All right, so acids and bases are also very important Let's try that one more time. Acids and bases are also very important inorganic molecules, okay? Acids and bases are also very important inorganic molecules. And acids and bases all fall on a scale that we refer to as the pH scale. The pH scale is how we measure how acidic or how basic something is. Okay, you may also hear the term alkaline used. Alkalinity is a measure of basicity, going actually the other direction on this particular chart, going towards 14. So let's just lay all this out and make sure that we're on the same page, because that seems confusing. The pH scale measures how acidic or basic something is. Okay, how acidic or basic something is. The scale runs from 0 to 14. 14 is basic, 0 is acidic. 7 in the middle is neutral water. Okay, this is good old-fashioned distilled water, pH of around 7. Okay, as I go lower in number, 6, 5, 4, 3, I'm getting more acidic. Like your stomach acid, that's like a pH of 2. It's very acidic indeed. You get a lemon that you're going to put in your sweet tea and you give it a lick, that's a pH of around 2. It's quite acidic. Okay, it's quite acidic. Whereas on the opposing side of the spectrum, 9, 10, 11, 12, think about like ammonia-based products, like that would be found in your ureic outputs, urine outputs. That's not a good example because urine is actually acidic, but for reasons that we are not going to get into here. But ammonia itself is quite basic. Any household cleaners, you run the gambit, man. There's all sorts of interesting things going on here. The idea is that this is a logarithmic scale. What that means is from one number to the next is 10 times the variation. That is really important. What that means is that each of these numbers is very dramatically different from one another. So when you look at your blood, okay, your blood's pH is around 7.4, is what it's supposed to be, yeah, around 7.4. That's actually a pretty good margin away from 7, okay? 6 versus 7, 5 versus 4, they're 10 times different from one another. These are huge numbers, okay, big numbers. It's a logarithmic scale. They are very different. Basic, acidic, okay? 0 is super acidic, would burn through this wall. 14 is incredibly basic. All right, that'll work. Let's go here. All right, I'm just going to give you some good examples of acids and bases that we deal with in our daily lives. That's really what I'm concerned with at this stage, provided no one else comes wandering in. All right, you know that you have stomach acid. Stomach acid assists with breakdown of food products. The stomach acid helps to neutralize any bacteria that might be coming in via the food that you're consuming. We have stomach acid. It's very important to our daily lives. Your blood. Okay, your blood is on a mild level of basicity, about 7.4. Your ureic output tends to be acidic, which guards you against bacterial invasion via the urethra. Urinary tract infections, pretty rare in the grand scheme, because as bacteria try to get in via your urethra, the urine you're releasing is constantly cleansing that with its acidity. All right. We use acidity and basicity in our bodies every single day. If you ever had like stomach acid issues, like acid reflux or what have you, you take antacids. What those are bases that neutralize the acidity of your stomach acid, or mildly so. I mean, shoot, man, we do this all day long. When we break down alcohol, one of the things we break it down into is an acid. When we use our musculature, one of the chemicals released as a result of flexing your muscles is acetic acid. Okay, it's a breakdown product of what's called acetylcholine. Acetic acid is an acid. All right, so, lactic acid from flexing your muscles. Like, we can do this all day long. These are very important. And then, of course, there are the organic molecules. And man, you need to be best friends with this stuff. This is very important. The rest is nice. This is very important. Proteins, carbohydrates, lipids, and nucleic acids. These are big carbon-containing macromolecules, okay, large molecules. Let's see, where do I want to start here? Let's just start at the top and work our way down. So first things first, we got to get the terms polymer and monomer out of the way. A polymer is a chain, if you will, of many monomers put together. A monomer is a building block, and if you put several of them together, you can make a chain that we call a polymer. Polymers are long strings of monomeric building blocks. They're subunits. In other words, starch is a blank of many glucose what? Starch is a polymer of lots of glucose monomers, okay? Monomers and polymers. And that brings up another term set that you should be friends with at this stage. Those terms are dehydration synthesis and hydrolysis or hydrolysis, okay? Dehydration synthesis means to make something by removing water. What we're doing there is we are building polymers. By comparison, hydrolysis means to break something down by adding water back to it. Hydrolysis, we're breaking something down. You take a polymer and you break it down into its monomeric subunits. If I take starch and I break it down into glucose molecules, that is hydrolysis. That is what salivary amylase does, okay? It's an enzyme in your digestive system that breaks down starch. When you eat starch, the starch molecules are simply too big to get into your bloodstream. So what do you have to do? You got to break that starch molecule down into its monomers. You got to put it through a hydrolysis-based process and break it down into individual glucose molecules, which are then small enough to get into your bloodstream. This is so important. I can't get across to you. It's just so important. All right, let's see. Got on a tirade there, man. Now I got to focus on what the heck I'm doing. Okay, we're on the sugars. Carbohydrates. Anytime you hear carbohydrate, you need to be thinking sugars. And in the realms of sugar, the smallest sugars that we have are referred to as the monosaccharides. And the key monosaccharides look as follows. These are glucose, which is your blood sugar. Blood sugar is glucose. Glucose is blood sugar. Fructose, galactose, deoxyribose, and ribose. Deoxyribose and ribose being very important to your genetics. Okay? When I say that you store your genetic code as DNA, DNA stands for deoxyribonucleic acid. Ribose plays a role in this. All right? Ribose plays a role in it. It's so important. So let's look at how this is done. All right. There are also disaccharides out there. So if these are monosaccharides, monosaccharide, it means one sugar. Mono is one, saccharide is sugar. There are also disaccharides. Disaccharides is when you take two monosaccharides and bind them together to make a single unit. Like, for instance, here we have sucrose. Sucrose is good old-fashioned white table sugar, okay? Put it in your coffee, white table sugar. You make sweet tea. You use sucrose, all right? Sucrose is a combination of a glucose molecule and a fructose molecule. Now, how is it a combination of them? You take glucose, you bind it to fructose, you synthesize sucrose from them. That is dehydration synthesis. That process removes water from here, as you can see there, in hydrogen and oxygen and hydrogen, H2O. You pull the water out, you make sucrose. Sucrose is a standalone compound now. This can then be broken back down into glucose and fructose by using hydrolysis-based enzymatic reactions. You do this, okay? You do this. You build things via dehydration synthesis, you break things down via hydrolysis. Yes, that'll do. All right, let's talk about a couple other disaccharides just for fun. There's also maltose down here. You may be familiar with maltose. You may have heard of malted barley. This is one of our brewing sugars, okay? And then by comparison, we have lactose here. Lactose is the sugar found in mammalian milk, okay? Somebody's lactose intolerant. One of the things they struggle with is dairy products, okay? Lactose. Lactose is very important. All right, carbohydrates, the polysaccharides. Polysaccharide. Now look at this, folks. Monosaccharide, one sugar. Disaccharide, two sugars. Polysaccharide, poly means many. Many sugars. Many sugars. Thousands in most cases. Okay, the big polysaccharides can contain lots of molecules, okay? Lots of individual monosaccharides. Now, I hear footsteps out in the hallway, and I'm constantly wondering who's out there. They're doing something on the floor. It's driving me up the wall. We just try to focus. The polysaccharides. Okay, there's a lot of different polysaccharides in the world around us. Cellulose is a polysaccharide found in plants. Starch, as I just mentioned, is a polysaccharide. Chitin in the hardened exoskeletons of crustaceans. Like, there's all sorts of different polysaccharides out there. Lots and lots and lots. But important to us is glycogen. Okay? Glycogen is important to you because glycogen is how you as a mammal store sugars long term. So the way this works is kind of like this. Okay, you've got blood sugar that you use on a moment-to-moment basis to make ATP. Okay, blood sugar constantly being utilized as an energy source. That's what it's there for, is to provide energy for your cells. But what if you have too much blood sugar? Well, you release insulin, right? Insulin brings your blood sugar levels down. What insulin really does is it signals your liver most of the time to make glycogen. Glycogen is when you take many lots of glucose molecules and you bind them together into a single larger molecule. It's typically stored in the liver. It's called glycogen. All right, called glycogen. Now, why do you do that? Why would you do this? Because the glucose molecule is small and mobile. But what if you bind it all up into a single huge molecule? This stays put in whatever cell it's found in. So if you make lots of this in the liver, it's going to stay in the liver until you go many hours without having anything to eat. Your blood sugar levels start to drop, so you release a different hormone, and that signals for the hydrolysis, the breaking down of glycogen, and you start trickling out glucose back into the bloodstream to maintain your blood glucose levels around 70 or 80 milligrams per deciliter. Your liver is like a bank. Got extra glucose? Store it in the liver. Need some for a rainy day? Pull it out of the liver. That's how this works. It's amazing. What a beautiful system. I got chill bumps. Love this kind of stuff. Brings a tear to your eye. It's a beautiful, elegant dance. All right, let's go here. Lipids, the lipids. What do I want to say here? Yeah, let's just take a shot at it. So lipids are things like fats and oils. Okay, fats and oils are lipids. There's also some kind of neat stuff in there as well. Some phospholipids that make up parts of your cell membranes, which we'll talk about here in a second. Steroids. Like when I say steroid, you have some idea of what I'm talking about, I predict. Steroids are also lipid in their basis. But the good old-fashioned lipid of choice, when you're talking about lipids, is referred to as being a triglyceride. Triglyceride, that is a glycerol backbone with 1, 2, 3 what are called fatty acid tails. That makes it a 1, 2, 3 triglyceride. A triglyceride looks like this. It is a glycerol molecule with chains sticking off the back of it. And this is important because I'm willing to bet you've heard the terms saturated fat and unsaturated fat. Now let me tell you what this means. A saturated fat is one where the tails of the triglyceride molecules are all saturated with hydrogen. They're packed with hydrogen, no double bonds, all covered in hydrogen. And because they are saturated, the tails are straight. By comparison, if there are any double bonds in place, that would be considered an unsaturated fat. The tail would be kinked. So instead of all straight, one's kinked. Or 2 or 3 can be kinked. They can be monounsaturated, polyunsaturated, you name it. The idea is that if the tails are straight, that means it's saturated with hydrogen. If the tails are kinked in any way, shape, or form, that would be considered unsaturated. Now, what the heck does this all mean? Saturated fats, you ever play Tetris? You know the long pieces are real easy to stack up? Saturated fats tend to be solid at room temperature. Okay, think about butter. Okay, think about lard. You throw some bacon in a pan, you cook it up, leave the pan on the oven top, walk away, come back after lunch, and it's solid. You know, kind of gooey, but solid all the same. Because saturated fats tend to be of animal origin. Okay, these are animal fats. Unsaturated fats tend to be very difficult to stack. okay, because they got these kinked tails. They don't really stack up on one another molecularly. So these tend to be liquid at room temperature. Unsaturated fats tend to be things like olive oil or canola oil or what have you. These tend to be of plant origin, okay? Unsaturated fats tend to be of plant origin. Saturated fats tend to be of animal origin. And there's a little bit more to discuss here. Let's talk about trans fats and omega-3 fatty acids. How much do I want to talk about it? That's the question. Let's just keep this simple, shall we? My first comment to you is this. You need lots of omega-3 fatty acids in your system. They are very heart healthy. They regulate your system. They are important. You need to be having at least 1, maybe 2 meals that are fish-based in a week, or be taking fish oil pills. I buy cheese and milk and bread that are all enriched with omega-3 fatty acids. This stuff is available and it'll keep you healthy. They say an apple a day keep the doctor away. Maybe, but if you'll eat more omega-3 fatty acids, you'll be even better off, I assure you, okay? You need lots and lots of omega-3 fatty acids. As it's coming out that this stuff's actually way, way better for us than we thought beforehand. So even huge doses, is considered to be very beneficial. Some cutting edge work I was listening to the other night. By comparison, there are also trans fats. Now, trans fats are something else. Trans fats are manufactured in a laboratory. What you do is you take a cis fatty acid tail. You've heard the term cis and trans, I predict, before, but you probably don't know what they actually mean. Cis and trans are ways of referring to the shape of molecules in 3-dimensional space. Okay, like a cis molecule might look like this. Okay, you got your hydrogens kind of sticking off the ends of the carbon chain here in the middle. So a cis molecule would look something like this. And then the trans molecule will be almost like a mirror image. It'd be rotated in one axis. Okay, so there are cis fatty acids. This is what they look like in nature. This is the natural form of a double bonded, kinked-tailed fatty acid chain. This would result in an unsaturated fatty acid. But what we can do is we can do what we call partial hydrogenation. There we go. They can become partially hydrogenated. If you go and you look at some of your baked goods in your cabinet right now, you could probably find some that say partially hydrogenated. And what that means is they bubble hydrogen through a bath, and it changes this cis fatty acid molecule. It basically twists it, causes it to twist and form a trans fatty acid. This is not natural. This is only manufactured in a laboratory setting. Trans fatty acids are not found in nature. And because trans fats are not found in nature, we have no enzymes that are capable of breaking them down. And because we have no enzymes that are capable of breaking them down, you can make baked goods that have an eternal shelf life. Okay? And if you're a major corporation and you can guarantee your foods will last longer on the shelf than anybody else's, you're going to sell more of those products. But there's a downside to this. No natural enzymes to break it down. What happens when it gets into your system? It just gets in your bloodstream, stays there. And the longer you have lipids of this fashion cruising around your bloodstream, the higher your risk of cardiovascular disease, like atherosclerosis. Trans fats run a direct line to atherosclerosis. They are incredibly dangerous, as it turns out. Incredibly dangerous. It's scary too, man. Quick story. So you guys may know about a restaurant chain, fast food, referred to as Bojangles. Okay, went to a Bojangles in North Carolina years ago. I got a bunch of hash browns. And I pulled out, and when I pulled out, somebody kind of tried to T-bone me, and I had to hit my brakes, and my friggin' hash browns just went everywhere, all over my car. Like 8 months later, I found one of them that had just been sitting there the whole time. Just sitting there. I picked it up and looked at it. You wouldn't have known it wasn't fresh. The only thing you could tell is it was cold and dehydrated because all the water had left it. It was completely untouched by bacteria. Scary, man. It's not natural. So all of this culminates in the following. The FDA, upon finding that trans fatty acids are in fact quite dangerous, comes out with a statement. Now, if you're familiar with government doublespeak and how we have to phrase things to not get sued by food lobbies and general libel lawsuits, the FDA statement about trans fats is that trans fats are not generally recognized as safe. Okay? In other words, stay the hell away from trans fats. If you can keep from it, man, they are very dangerous and will lead to your heart having blockages. You will have problems if you consume trans fats over a large or long period of time. It's like if you smoke all the time, you're just begging for lung cancer. Well, if you're eating lots of trans fats, you're begging for open heart surgery. All right, let's go here. Phospholipids. All right, man, I wish I had something to drink. All this talking. Phospholipids. Phospholipids make up your cell membranes. Okay, your cell membranes are made of phospholipids. Phospholipids look just like triglycerides. They've got a glycerol molecule, one fatty acid chain, two fatty acid chains, but instead of a third one, you flip the molecule over and you stick a phosphate group on it. Now that's fascinating. That makes phospholipids quite weird, man. A strange molecule and pretty freaking cool from my perspective. One of my favorites, okay? You see, lipids tend to be nonpolar. They're nonpolar covalently bonded. And as a result of that, oil and water don't mix, right? But a phospholipid molecule has a nonpolar end that acts like a lipid, and then they have a polar end. And this polar end is capable of binding to water. So, your cell membranes are referred to as being a phospholipid bilayer, right? A phospholipid bilayer. What that means is you have two layers of phospholipids. You've got this hydrophobic tail section where the oily parts, the hydrophobic parts, hydrophobic means water-fearing, the oily parts, the nonpolar bits, they connect to one another and hold strongly, and then the top surface and the inner surface of the cell, like this would be down where the nucleus is, and that's the outside of the cell. The inside and the top, these head portions here, these heads are going to be polar. They're polar covalently bonded, which means they are capable of binding to water found elsewhere in your body. So, take-home message, if I'm a nonpolar molecule and I'm trying to get into a cell, I can't get through the top layer. But what if I'm a polar molecule? I can get through the top layer, but I can't get through the middle. Phospholipids are the reason, or one of the reasons, that your cells are considered differentially permeable, okay? Or selectively permeable. This is very important. These are going to be found in your cell membranes. All right, steroids. Steroids are all manufactured from cholesterol in the grand scheme of things. So cholesterol, as you know, is a lipid. And if I were to poll all of you right now and ask you if cholesterol is good or bad for you, you would probably all say that cholesterol is bad, but the reality is that cholesterol is very important for us, okay? We have to have cholesterol to make sure that our cell membranes stay fluid. We have to have cholesterol to build steroid molecules. Now, when I say steroids, a lot of you, I hope, are probably thinking about professional sports, because that's where we hear about steroids all the darn time. Either that or a medication you've taken. The reality is that cholesterol is a precursor to all sorts of different steroid hormones, okay? Like testosterone and estrogen. Testosterone and estrogen drive our male and female secondary sexual characteristics. This is what allows us to reach our reproductive state, if you will, to reach a capacity for reproductive success. We must have cholesterol as a building block to be able to manufacture estrogen and testosterone for puberty to do what it does. Okay, it's incredibly important. Oh, there's a good story to tell here. I don't know if we're going to have the time though. Vitamin D. Let's just go there. Play your cards right and I'll tell you a good story some other time. Vitamin D is also a steroid hormone, and you have to have vitamin D to live, man. Vitamin D is so important. When you go and you look at the milk at Publix, it's going to say enriched with vitamin D. And the reason that it's enriched with vitamin D is because vitamin D is absolutely quintessential. It's of the utmost importance for you to have the capacity to absorb calcium into your bloodstream. You can't get calcium from the foods you eat unless you have vitamin D. Now, normally we make vitamin D using sunlight, but we're not outside very much these days, so we can't do that. So we get our vitamin D from the foods that we eat. We tend to enrich foods that are rich in calcium with vitamin D artificially so that we can absorb that calcium. So if you go look at orange juice or milk or cheese, a lot of the time they're enriched with vitamin D. Yeah, proteins. All right, in the realm of proteins, I want you to know the following. These are super important for us. When I see you, okay, your skin, that's protein. Your hair, that's protein. Your eyes are protein. Your muscles are protein. Protein runs, it's your enzymes, the contractile bits of your muscles, your oxygen carriers like hemoglobin within your system. It's all protein. Protein is very, very important for us. And its building blocks are called the amino acids. Do I have peptide on here anywhere? Well, let me just lay it out here for you if I don't. It doesn't seem like I do. Anytime you hear the term peptide, a peptide bond, peptide, anything peptide, P-E-P-T, peptide, that is referring to binding amino acids to build proteins. Proteins are referred to as being polypeptides. Okay, they're groups of many amino acids. Amino acids are the building blocks of proteins. Now, proteins come in a variety of structures. They tend to be initially made as a string, referred to as a polypeptide. This is also called the primary structure of a protein. This is very important. You need to know this. The primary structure of the protein can then be changed. It can be turned into what's called a beta-pleated sheet or an alpha helix. A beta-pleated sheet is when you take your long string of polypeptide and you align it like this to make a sheet that kind of sticks together. How do these stick together? Well, proteins have all sorts of polar bonds internally. They display lots of polarity all over the place. And they kind of will then stick to one another. So one primary strand, one polypeptide will stick to adjacent strands through what we call hydrogen bonding. Hydrogen bonding. Beta-pleated sheets where you align these strings like this and form a sheet. The little bits are held together via hydrogen bonding. Now these are covalent bonds between amino acids, but you can put this thing and stick it together, and these weak attractions, even in this alpha helix here, these are all going to be hydrogen bonds. So what's the importance of hydrogen bonds? Hydrogen bonds help us to form our different protein shapes that lead to their functions. Proteins only work if they're in a very specific shape, and those shapes are held together by hydrogen bonds. I got to keep going on this. This is important. Denatured. This is an important term. If you grab something hot, you will burn yourself, and you'll see damage to your skin surface. That is denaturing protein. If you go and buy a steak and it's red, and you chuck it on the grill and it turns dark, it's turning dark because you're denaturing the protein within it. To denature means to bust up the hydrogen bonds that hold those proteins in their unique shape. Turns out that's pretty easy to do. It'd take a lot of work. So proteins, the individual amino acids are held together via covalent bonds, but their unique shapes, like a beta-pleated sheet or an alpha helix, those are held together via hydrogen bonds. And then you can take this and further wrap it up and form what's referred to as a tertiary structure. These are secondary structures. You can form a tertiary structure. You can take several tertiary structures and bring all those together to form a quaternary structure. These would typically be functional proteins at that stage. Those would be functional proteins. And then, I think last but not least, we have the nucleic acids. Nucleic acids store your genetic code. Here's the fun part. You know what your genetic code is actually? Your DNA? It's just a code for how to make proteins. That's all it is. There's nothing fancy. Your chromosomes, they're cookbooks. Your chromosomes are cookbooks to how to make protein. It's very simple in reality. All right, so let's talk about it. So nucleic acids are important. They are what make up your DNA and RNA. DNA and RNA. These are important because they store the code for how to make proteins. Their building blocks are called the nucleotides, and in the realm of nucleotides, there are 5. The big ones are called purines, and they are referred to as adenine and guanine. The small nucleotides are referred to as being the pyrimidines, and they are cytosine, thymine, and uracil. Cytosine, thymine, and uracil. Now, in the realm of nucleic acids, again, there are 2 for our purposes. These are DNA and RNA, and DNA and RNA are quite different from one another. DNA, deoxyribose nucleic acid, versus RNA, ribose nucleic acid. DNA, the sugar is deoxyribose. RNA, the sugar is just ribose. DNA is found inside the cells. DNA is very large. DNA is a double helix, okay? Real big, always inside the nucleus of your cells. RNA does its job outside the nucleus. RNA tends to be single-stranded. RNA uses uracil in place of thymine. This nucleotide base pairing sequence, you find thymine in deoxyribonucleic acid, you find uracil in ribonucleic acid. Your nucleotides are very important for storing your genetic code. And when I say storing your genetic code, what I'm really saying is storing the code for how to make the proteins you need to survive. And that's that, folks. That's that. That's our first lecture. So that gets us through the introductory materials and basic chemistry. I'm pretty happy with it. So thank you so much, man. You're going to thoroughly enjoy this. I hope you've enjoyed this as much as you possibly can. I'll be putting up a quiz on this material, and you'll have a week to do it. All right, thanks so much, guys. Have a good day.